In this video, we'll extend the concept of finding the area between the x-axis and the graph of a function to finding the area between the graphs of two functions. To the right over here, we have a graph of f of x equals x plus 2, it's a linear function, and g of x equals x squared minus 4x plus 6. Now, our task will be to find the area that's trapped between these two functions right here. Now, here's how we're going to proceed. As we did when we were finding the area underneath a curve, we're going to start by segmenting this entire region here with rectangles. We'll slice and dice and draw rectangles. They could be left, they could be right, it doesn't really matter which. And we'll pick one of them to discuss. We'll look at this one right here. I'll draw one in as neatly as I can. Okay, so there we go. Have a nice, happy little rectangle. And we'll put that rectangle out here at some distance out along the x-axis, and we'll say that's x equals x sub I. Now, as we did with area between the graph and the x-axis, we need to figure out some way of calculating the area of that rectangle. And we know the area of that rectangle is the height times the width. Now, typically, what I try to remember to do is to tag these corner points right here where the rectangle touches the curve. So I want to tag those 2 points right there. This point here is out some distance. We called it x sub I. And the height of this point up right here, well, we know that's a point on this graph, g of x, so its height is g of x sub I. So there's the coordinates of that point, x sub I, g of x sub I. Likewise, this point also is out the same arbitrary distance that we called x sub I. And the height of this point on the y-axis is, well, again, it's on the function f, so the height is whatever the function height is at this x value. So that would be f of x sub I. And those are the coordinates of those 2 points. Now, that's fairly useful because knowing the coordinates of those points now, I can come over here and talk about this height, right, or this distance right here, which is the height of the typical rectangle. Okay? And we'll give that an algebraic expression. The height of this typical rectangle is the difference in these two y values. If this were up 8 and that were up 6, then we would know this distance is 8 minus 6, or 2 units. But we don't know exactly how high that is because we don't really exactly know where x sub I is. But we do have this height right here. F of x sub I represents how high off the x-axis that point is. G of x is the height of this point. So if I find the difference of those, f of x sub I minus g of x sub I, that's the height of this typical rectangle. Now, as we did when we were finding area underneath a curve, we need to consider the width of this typical rectangle, and we know that that's called delta x. So now the area of the ith rectangle, a sub I, is the height, which is f of x sub I minus g of x sub I, multiplied by the width, delta x. And if we can find the area of one rectangle, then certainly we can find the area of all of the rectangles that we could draw in that region and add them up. And that sum would look like this. Be the sum of f of x sub I minus g of x sub I times delta x. And this could be a left sum or a right sum or some other sum. We'll make it a right sum, so we'll let I vary from 1 to n. And we know if we take the limit of this Riemann sum as n increases without bound, this sum becomes a definite integral. So we'll write that next. Now, one thing that we may want to do is we may want to go ahead and simplify this. And we can do that now, or we can go ahead and write the definite integral. We'll do it that way. The integral is of f of x minus g of x, and we're integrating with respect to x. Now, a word about the bounds. These two functions are very easy to graph by hand, and very clearly they intersect at x equals 1 and up here at x equals 4. So very clearly from this graph, we're integrating from 1 to 4. That's our bounds of integration. If the graph were not well behaved, if it crossed somewhere out in the middle or something like that, then we could certainly use our graphing calculators and the intersect command found under second trace. It's, I think, option number 5 under second trace. We could find the x coordinates of these intersection points, and those would be our bounds of integration. And because the College Board requires 3 decimal places, we'll be of that habit. If we happen to find these intersection points using a graphing calculator, then we'll round these values to 3 places after the decimal. Now, another recommendation, I always suggest write down what you mean here. This is the integral from 1 to 4 of f of x is x plus 2, and then g of x minus the entire quantity, so I'm going to use a parenthesis here, x squared minus 4x plus 6 dx. And if you'd like to distribute the negative through there and simplify that, that's fine. Likely as not, you have these functions stored in your graphing calculator. If you were graphing this to see what the graph looked like, you probably have this stored under y1, perhaps, and perhaps you have this stored as y2. And if you have those functions stored, then there's no sense in resimplifying this expression or doing anything else, because we're going to use the graphing calculator to evaluate this interval. The calculator will return a value of 9/2, I believe, or 4.5 for this area. And the way that I did that, again, is I used the function integrate command. I would not type this, write this down on my worksheet, but for your benefit, math 9, function integrate, and the parameters are the stuff. In this case, it's this function minus that one, and assuming that you have those stored, you can actually type y1 minus y2. And remember, these are under the vars menu, vars, then arrow to the right to y variables, then function, and then pick the y1 or the y2. Don't forget we're telling it to integrate with respect to the independent value x, and the bounds of integration here are 1 to 4. Now, if you'd like to have 9/2, and this is a good habit probably to be in, if you'll go back to the math menu and choose math number 1, you'll get the little diamond to a fraction. And that'll give you a fraction answer out, and the calculator will return 9/2 as your answer. So, summary, to find the area between the curves, always draw a decently sized picture. Go in and sketch up your typical rectangle and tag these corner points so that you can very quickly see that the height of this typical rectangle is this value minus this value, top minus bottom. So in this case, f of x sub I minus g of x sub I. Then set up your area of the ith rectangle, and then transform that through a sum into a definite integral like this. And then from here down, we're using our calculator. We probably would go ahead and write the functions back in there. Be careful that you use parentheses right here to separate this function. But then from there, we punch it up into our calculator, and we get our answer. And that's all there is to finding the area between the graph of two functions.